Hello everyone. Welcome back to my course Fundamentals of Thermodynamics, Essential Knowledge for Engineers. In this video, we will talk about standard atmospheric model. Also, I will be thankful if you give me feedback about this course to make it better and more useful for you. Please write down your thoughts in the comment section or reach out to me via the email provided in my profile. The Earth's atmosphere is like a very thin blanket of air that wraps around the planet. To imagine just how thin it is, picture the Earth as the size of a basketball. The atmosphere would be no thicker than a tightly held pillowcase. Gravity acts like an invisible hand, holding this blanket close to the Earth's surface. Even though it seems light and fragile, the atmosphere is the stage for incredibly complex processes involving chemistry, heat, and fluid motion. These processes constantly change, creating the weather we see every day. The way the atmosphere behaves also changes as we move upward. The sun heats the ground, which in turn warms the air directly above it. Think of it like heating soup. The hot liquid near the bottom rises while cooler liquid sinks. Similarly, warm air rises and mixes with cooler air higher up, a process called convection. This means temperatures are usually highest near the surface and decrease as you climb in altitude. The speed of sound in the air depends on temperature, so it also slows down as you go higher. Air pressure, which can be thought of as the weight of the air pressing down on you, decreases with altitude because there is less air above. Density, or how packed the air molecules are, also decreases because it depends on both temperature and pressure, as described by the ideal gas law. For aircraft designers, understanding air density and how it changes with height is critical, because aerodynamic forces depend directly on it. To make this easier, scientists created standard atmosphere models. These models act like a cheat sheet, showing the average changes in temperature, pressure, and density with altitude. There are several versions of these models: standard, hot, cold, and tropical, and they are updated periodically to include the latest measurements. The models are based on real atmospheric data, averaged and fitted to equations, and they assume that temperature and pressure change only with altitude, ignoring day-to-day weather or location. The standard atmosphere model divides the atmosphere into three main layers, each behaving differently. The first layer, the troposphere, stretches from the Earth's surface up to about 11,000 meters. In this layer, temperature decreases steadily as you go higher, much like how it gets cooler when you climb a mountain. The temperature at any given height can be calculated as 15.04 degrees Celsius minus 0.00649 times the height in meters. Pressure continues to decrease with altitude and can be calculated as 101.29 kilopascals, multiplied by the ratio of the temperature at that height, plus 273.1 divided by 288.08, and this whole ratio raised to the power of 5.256. The second layer, called the lower stratosphere, extends from 11,000 to 25,000 meters. In this region, the temperature stays nearly constant at negative 56.46 degrees Celsius, like a plateau on a mountain where the air temperature doesn't change much. Pressure continues to decrease with altitude, but it does so exponentially. Pressure continues to decrease with altitude, following an exponential decay, and can be calculated as 22.65 kilopascals multiplied by the exponential of the number 1.73 minus 0.00157 times the height in meters. The third layer, the upper stratosphere, begins above 25,000 meters. Here, the temperature actually starts to rise with altitude, because this layer absorbs ultraviolet light from the sun, similar to how sunlight warms the top of a swimming pool. The temperature at a given height can be calculated as negative 131.21 degrees Celsius plus 0.00299 times the height in meters. Pressure decreases with altitude and can be calculated as 2.488 kilopascals multiplied by the ratio of the temperature at that height plus 273.1 divided by 216.6. And this whole ratio raised to the power of negative 11.388. In every layer, density can be determined from the ideal gas law as the pressure divided by the product of 0.2869 and the temperature at that height plus 273.1. We will learn about the ideal gas law on our next lessons. All of these values were given in metric units. Now I will give you the same values, but in English units. As we said before, the standard atmosphere model divides the atmosphere into three main layers, each behaving differently. The first layer, the troposphere, stretches from the Earth's surface up to about 36,152 feet. In this layer, temperature decreases steadily as you go higher, much like how it gets cooler when you climb a mountain. The temperature at any given height can be calculated as 59 degrees Fahrenheit minus 0.00356 times the height in feet. Pressure continues to decrease with altitude and can be calculated as 2,116 pounds per square foot, multiplied by the ratio of the temperature at that height plus 459.7 divided by 500, 18.6, and this whole ratio raised to the power of 5.256. The second layer, called the lower stratosphere, extends from 36,152 feet to 82,345 feet. In this region, the temperature stays nearly constant at negative 70 degrees Fahrenheit, like a plateau on a mountain where the air temperature doesn't change much. Pressure continues to decrease with altitude, following an exponential decay, and can be calculated as 473.1 pounds per square foot, multiplied by the exponential of the number 1.73 minus 0.00048 times the height in feet. The third layer, the upper stratosphere, begins above 82,345 feet. Here, as we said, the temperature actually starts to rise with altitude, because this layer absorbs ultraviolet light from the sun, similar to how sunlight warms the top of a swimming pool. The temperature at a given height can be calculated as negative 205.055 degrees Fahrenheit plus 0.0164 times the height in feet. Pressure decreases with altitude and can be calculated as 51.97 pounds per square foot multiplied by the ratio of the temperature at that height plus 459.7 divided by 389.98, and this whole ratio raised to the power of negative 11.388. In every layer, density can be determined from the ideal gas law as the pressure divided by the product of 1,718, and the temperature at that height plus 459.7. By using these models, engineers can predict how an aircraft will perform at different altitudes. It's like having a map of the atmosphere, showing how air feels at various heights. This knowledge ensures that aircraft can fly safely and efficiently, whether they are cruising near the ground or at the edge of the stratosphere. For comparison, we'll examine Mars' atmosphere so we can gain a clearer understanding of how Earth's atmosphere behaves. The Martian atmosphere is an extremely thin layer of gas, mostly carbon dioxide, that extends from the surface of Mars up to the edge of space. Compared to Earth, Mars' atmosphere is much less dense, but there are still several similarities. Gravity holds the atmosphere close to the Martian surface, and within it, complex chemical, thermodynamic, and fluid dynamics effects occur. Just like on Earth, the atmosphere is not uniform. Properties of the gas change constantly with time and location, producing weather patterns on Mars. These variations extend upward from the surface. The sun heats the Martian surface, and some of this energy warms the gas directly above it. This heated gas then moves upward through the atmosphere through diffusion and convection. As a result, the gas temperature is highest near the surface and decreases with altitude. The speed of sound depends on temperature and likewise decreases as altitude increases. Just as on Earth, atmospheric pressure decreases with altitude, and the density of the gas depends on both temperature and pressure through the equation of state, decreasing as you go higher. Aerodynamic forces such as lift and drag depend directly on gas density. To assist engineers and aircraft designers, a mathematical model of Mars' atmosphere has been created to capture how these properties change with altitude. This model is based on measurements from the Mars Global Surveyor in April 1996. The data was collected by Jonathan Donady of Canfield Middle School during a cyber mentoring program in 1999 and then curve-fitted into equations by Dave Hiltner of St. John's Jesuit High School as part of a shadowing program in May 1999. The model has two parts. The first part describes the lower atmosphere, extending from the surface up to 7,000 meters. In this layer, temperature decreases gradually with altitude. Temperature is equal to -31 minus 0.000998 multiplied by altitude. Pressure is equal to 0.699 multiplied by E raised to the power of -0.00009 multiplied by altitude. The second part describes the upper atmosphere, which begins above 7,000 meters. In this layer, the temperature continues to decrease with altitude. Temperature is equal to -23.4 minus 0.00222 multiplied by altitude. Pressure is equal to 0.699 multiplied by E raised to the power of -0.00009 multiplied by altitude. In both parts of the Martian atmosphere, pressure and temperature are obtained from curve fits, while density is derived using the ideal gas law. Density is equal to pressure divided by the product of 0.1921 and the sum of temperature plus 273.1. Now, I will do the same thing for Mars' atmosphere and convert the values from metric to English units. The first part covers the lower atmosphere, which extends from the surface to 22,960 feet. In this layer, temperature decreases with altitude. Temperature is equal to -25.68 minus 0.000548 multiplied by altitude. Pressure is equal to 14.62 multiplied by E raised to the power of -0.0003 multiplied by altitude. The second part covers the upper atmosphere, which extends upwards from 22,960 feet. In this layer, the temperature also decreases. Temperature is equal to -10.34 minus 0.001217 multiplied by altitude. Pressure is equal to 14.62 multiplied by E raised to the power of negative 0.0003 multiplied by altitude. In each part, the pressure and temperature are curve fit, and the density is derived from the equation of state. Density is equal to pressure divided by the product of 1149, and the sum of temperature plus 459.7. Okay guys, now let's have a little quiz. The quiz consists of 5 questions. I'll give you 10 seconds for each one, and then I'll show you the correct answer. Let's start with the first question. Question 1. How does gravity affect the Earth's atmosphere? The correct answer is it holds the atmosphere close to the Earth's surface. Question 2. In the standard Earth atmosphere, how does temperature generally change in the troposphere as altitude increases? The correct answer is it decreases. Question 3. What is the main composition of the Martian atmosphere? The correct answer is carbon dioxide. Question 4. Why do aerodynamic forces depend on air or gas density? The correct answer is because density affects lift and drag on an aircraft. Question 5. In the Martian atmospheric model, what happens to temperature as altitude increases in both the lower and upper atmosphere layers? The correct answer is it decreases in both layers. Unlock the world of aerospace engineering with my other expertly designed courses. In Aerospace Engineering, Basics of Aviation Engines, you'll explore the different types of aerospace engines and how they perform, giving you a strong foundation in the propulsion systems that power modern aircraft. Then, take your knowledge to new heights with Aerospace Engineering, Aerodynamics and Structures, where you'll dive into the design and performance of aerospace structures and their aerodynamic behavior. Finally, expand your expertise with aerospace engineering, avionics, and aerospace systems, where you'll learn about the critical electronic systems that control and monitor modern aircraft, bridging the gap between engines, structures, and flight systems. Whether you're a student, aspiring engineer, or aviation enthusiast, these courses will equip you with essential knowledge to understand and contribute to the future of aviation. Join hundreds of learners and start building your aerospace journey today. Thank you guys for watching this video. If you have any questions about this lesson, feel free to ask me in the comment section. I will answer as soon as possible. We can continue to the next lesson and learn about fundamental properties of gases and air. See you in the next video. Bye.